Okay, in this problem I want to find the moment of inertia of this object, and this object that I'm going to look at is this thin disk that has a hole through the middle of it. And I'm going to tell you that the distance to the this inner diameter right here is going to be 0.125 meters. This distance to this outer diameter right here is going to be 0.25 meters. And the area, this disk is, this is the physical, this is the object I'm looking at. The hole is in the middle, and it's this thin-walled disk that has a thickness which is equal to 0.01 meters. Now, I also want to say the density is equal to 8,000 kilogram per meters cubed, and I want to find the moment of inertia about this point O right here. So if this is point G, which is the center of mass, point O is directly below the center of mass. Now, how do we find a moment of inertia like this? Well, typically when we want to look for moment of inertia, we're going to go to the table in the back of our book, and we're going to get an equation for the moment of inertia about a certain axis. However, we're probably not going to find the moment of inertia for this particular shape. And what I mean by that is we're not going to find the moment of inertia for this thin disk with a hole in the middle. However, we can use this equation for composite bodies. So if we have composite bodies, the moment of inertia of this body is going to be equal to the sum of the moment of inertia about the center of mass plus the mass times the distance to this axis squared. And this right here is just the parallel axis theorem. So it's just the sum of the parallel axis theorem. And now for us, in the problem we're looking at, we're going to get the moment of inertia of this big disk right here, and we're going to subtract it from the moment of inertia of this middle disk. So if we subtract these two from each other, the moment of inertia of this big disk minus the moment of inertia of this little disk, we're going to have this body right here, and we're going to have the moment of inertia that we're looking for. And I just want to draw in, this is the point O we're looking for. So this right here is the point O we're looking for. And if I call this part A and I call this part B, let's look at how we get the moment of inertia of part A. So in part A, if we go to the back of the book now and we look up an equation of the moment of inertia for a thin disk, we're going to get this equation. We're going to get that the moment of inertia through the center of mass is equal to 1/2 mr squared. And for us, we know what this r is. We know this r is going to be 0.25, but we don't know what this mass is yet. But luckily, we're given a density. And since density is kilograms, which is a mass, over meters cubed, which is a unit of length, or it's a volume, but it has a unit of length, we can multiply this by a volume, the density via volume, and we can get our mass. So our mass is equal to a density times a volume. And this is equal to 8,000 times this volume of this thin disk. Well, what's the volume? The volume is going to be the area of a circle. We know the area of a circle is pi r squared. So we have pi times 0.25 squared. And it needs to take into account the thickness. So the volume of a cylinder is pi r squared times the height. And our height is just our thickness. So our thickness is 0.01. And if we multiply this all out, we're going to get this is equal to 15.71 kilograms. Okay, so we now know what this moment of inertia about point about our center of masses. So this is the moment of inertia of our center of mass. But what we're looking for the moment of inertia of part A about point O, and this is going to be equal to the moment of inertia about the center of mass. So 1/2 mass, which is 15.71 times 0.25, which is our radius squared, plus our mass, 15.71 times the distance to this new axis, which is 0.25 squared. And if we multiply this out, we're going to get a moment of inertia of 1.473 kilograms per meter squared. So this is the moment of inertia of A right here. Now we just need to figure out what the moment of inertia of B is. So if we look at B, we're going to take the same steps. It's just a different size disk, and we're going to get the mass is equal to the density times the volume, and this is equal to 8,000 times pi r, and our r is just this 0.125 squared times this thickness of 0.01. And we're going to get a mass that's equal to 3.93 kilograms. Well, it's still a thin disk, so our moment of inertia about the center of mass is going to be, again, 1/2 m r squared. Our moment of inertia of point B of about point O is going to be equal to 1/2 mr squared plus md squared. And if we fill in the different pieces of information, this is going to be equal to 1/2 times the mass, which is 3.93, times the radius, and the radius of this disk right here is just 0.125, plus the mass, which is 3.93, times the distance to point O, and this distance point O is just this big diameter right here, or big radius right here, so it's 0.25 squared, and we get a moment of inertia of point B is equal to 0.276 kilograms times meters squared. Okay, so now we go back to this composite body we were looking at, and we say it's the moment of inertia of A minus the moment of inertia of B. Okay, so our final moment of inertia about point O is going to be equal to the moment of inertia A about O minus the moment of inertia of B about O. So this is going to be equal to 1.473 minus 0.276, and this is equal to a moment of inertia of 1.20 kilograms times meter squared, kilogram meter squared.